Okay, so I want to start by talking about the table of derivatives. So these are all things that you should have seen in Calculus 1. So this goes through all the basic rules, down through the quotient rule, the product rule, the chain rule, then the trig functions. You may or may not have every single one of these memorized. Probably these trig functions you should. The inverse trig functions, you almost certainly don't have all of these memorized. Tangent inverse comes up a pretty decent amount and is probably worth memorizing. Some of the other ones, we'll see how often they come up. Exponentials and logs. These are all things that you should know. There's not too much here to learn, but yes, you should definitely know these. Hyperbolics we won't do a ton with. I probably don't require these to be memorized, and the same for inverse hyperbolics. We might do some problems that use these rules, but I think that's something you can look up when the time comes around. Also, in your textbook, there's a thing for review of pre-calculus, and that can be pretty useful. We will use the binomial theorem in this class. Sines, cosines, tangents come up sometimes, not a lot. We do use these identities, especially these trig identities. These Pythagorean identities. Those come up quite often. The double angle and half angle formulas come up. I was hoping there was a unit circle in here, but there's not a unit circle in here. So anyway, all right, so with that said, thinking about those rules, some of the rules that we saw on that table of derivatives involved inverse trig functions. So obviously, if you know that the derivative of sine inverse of x is 1 over square root 1 minus x squared, then you know that the antiderivative of 1 over square root 1 minus x squared is sine inverse of x, right? So we can do integrals then that involve or that result in inverse trig functions. And we can be a little more generic because we don't just have to have sine inverse of x. We could do this for sine inverse u over a, right? So we have slightly more generic forms here. Integral du over square root a squared minus u squared is sine inverse of u over a. Integral du over a squared plus u squared is 1 over a tangent inverse u over a. And integral u square root u squared minus a squared is 1 over a secant inverse u over a. So when do you look for something like this? Well, something like this will come up when you have variable things squared and number squared kind of in your denominator, right? And then they're going to fit one of these forms. So that's just the thing that you kind of look for, right? So like if I had, 4 plus x squared, oh, well, then I know that a is 2, u is x, and I can use this formula to do my integral, right? Okay, so let's then go ahead and look at, well, they do a proof here by implicit differentiation. Feel free to read that if you want. At one point, I focused a lot on proofs in this class, and most people don't care. So, but if you want to see, proving this with implicit differentiation, you can see that here. All right, well, here they in this example, they do a definite integral 0 to 1, dx over square root 1 minus x squared. Oh, well, this is just exactly matching the form with a is 1 and u is x. It precisely matches the sine inverse form. So this is just sine inverse of x plus c, right? Except we're doing a definite integral, so sine inverse of x evaluated from 0 to 1. And then sine inverse of 1, sine inverse of 0. This might be a place to pull out the unit circle to do these. But there we go, pi over 2. Your calculator will also do these. All right. They have a little checkpoint here, which I'll probably ask you to do. So here's the next one. Evaluate the integral square root 4 minus 9x squared is in the denominator. Okay, well, let's check that out. Oh, well, that obviously matches this first form again, right? But here a is 2 and u is 3x, right? So we can just fill in the form from there, right? If a is 2 and u is 3x, then you can just apply the formula. It works out directly. And you get what you want. Now, you could also do this with u substitution. But you can do it directly with the formula as well. So it just kind of depends on how you want to think about it. It really ends up being the exact same thing. All right, let's just look at one of these that involves an inverse tangent. Here they have integral 1 over 1 plus 4x squared. Well, if you go look back at the formulas, this clearly follows the second thing with a is 1 and u is 2x. So our integral is going to be just 1 tangent inverse. Our u here is 2x. So this is just tangent inverse 2x. Right, and you can see how that well, I lost it. Where did it go? Oh, it's right here. Tangent inverse 2x plus c. Right? Okay. Now, you can get into some slightly more entertaining ones. But, you know, the ones in here are pretty much just straight using the formula. On the homework and maybe in class, we will deal with some where you end up having, you do like a u substitution problem that, oh, so something like here, you can see some of these like 413, 414. This might be a problem where you do like u is tangent inverse 2t, right? And then this is its derivative, and then you're integrating u dt, right? So we'll do some problems like this. But for now, I think this is enough of a starter video for this section.